Next, let's talk about shifting. Previously, we introduced this equation. So this function means try to find index I in this expression and then replace it with n. So we have just found index I, so we replace it with n. So we obtain this equation. So this equation usually works okay, but if this expression n contains three variables, then this equation fails. So let's see why this equation fails if this expression n contains three variables. So remember that we start with sigma 0. So this function means that try to find the Brown index 0 here and then replace it with n. So for instance, if you have just 0 here, then it will be n. Now suppose that we have these lambda abstractions. Here we have I copies of these lambda binders. Then, when we start, we try to find the Brown index 0. But inside this lambda abstraction, because we have I copies of lambda binders, here you have to try to find index I. And in this example, we have index I. So this one will be rewritten as lambda. We have I copies of lambda binders, and instead of 0 now, you are trying to find index I. And this I is going to be replaced with n. And in this example, we have I. So what this means is that when you have lambda I comma n, you have actually passed through I copies of lambda binders. So you can imagine that whenever you have this one, you have I copies of lambda binders outside. So if you simply define this one as n, something is clearly wrong, because those three variables in this expression n should be now shifted because of these lambda binders. Of course, those variables that are not free, let's call them just local variables. Local variables remain the same, but all these free variables should be adjusted, should be shifted by I, because we have I copies of lambda binders. So what we want is, to summarize, what we want is, you don't want to copy n directly here. So let me remove this one. And just imagine that we have passed through I copies of lambda binders. So what we want is, you don't want to just copy n. Instead, find the free variables in n and shift them by I, because you have these I copies of lambda binders. So therefore, there should be some way to decide whether a given index denotes a free variable or not. And then if we find a free variable, an index that corresponds to a free variable, we are going to shift it by I, by adding I. So here's an example. We have two lambda binders, and we have this lambda abstraction, and we are going to apply this lambda abstraction to the argument lambda 210. So currently this index 2 pointed to this lambda binder, and this 1 pointed to this lambda binder, and 0 of course pointed to this enclosing lambda binder. Now suppose that if you have just 0 here, then things are easy. This is the red X. So what happens is you copy this lambda, you copy this lambda, and this is now gone. And you have to find index 0 and then substitute the argument for that. So in this example, this 0 becomes the argument lambda 210. So this is fine because this 2 this index 2 still points to this lambda binder, and this 1 still points to this lambda binder. So everything is okay. Now let's consider another example where now this time we have in addition to this the Brown index 0, this is the body, we have an inner smaller lambda abstraction lambda 1. So this points to this lambda binder, and because of this lambda binder, now 1 points to this lambda binder. So we are going to replace this one with the argument lambda 210, and we are going to replace this one, this index 1, into the argument lambda 210, and we copy this lambda binder. So if you literally replace these indexes 0 and 1 with the argument, you obtain this expression. But this is clearly wrong because these indexes are fine, but these two indexes are pointing to wrong lambda binders because of this one. So 2 is supposed to point to this one, but in fact it points to this one. And this 1 is supposed to point to this lambda binder, but actually it is pointing to this one. So why do we see this wrong result here? The reason is when we make a copy of the argument here, so we make two copies. The first copy, second copy. For the second copy here, it is placed inside this lambda binder. So all three variables here, you have to analyze this expression, and you have to find all three variables, and you have to shift it by 1 because of this lambda binder. If it is not a free variable, then if not free, then no change. So inside this expression, this is not free, but these two indexes denote free variables. So the correct answer is you have to shift it by 1. So this is 3, 2 should become 3, and 1 should become 2, while this index remains 0. So this is what we want. So from this example, let's try to define a new function for shifting free variables. So we'd like to fix this equation. So let's start with this one. Sigma I n. So the meaning of this function is try to find index I and replace it with n. But we have just found index I, so this is going to be n. But we learned that this equation is wrong because it doesn't account for free variables that should be shifted by I. So imagine that we have I copies of lambda binders here. Instead, we want to introduce another function tau. So we'd like to write a tau n with superscript I. So this function means find all free variables in n and shift them by I, that is add I. Then how can we tell whether a given index denotes a free variable or not? In the beginning, all indexes are free variables. In other words, every index greater than or equal to 0 is counted as free. So we use 0 here. So this 0 means any index, because any index is greater than or equal to 0, is counted as free. To see why we need this another subscript here, let's consider this one, tau 0 I lambda n. So according to the definition here, it means that try to find the free variables, and free variables have index greater than or equal to 0, and these free variables will be shifted by I. Now we want to move this tau function inside this lambda abstraction, so you have tau I n. But inside this lambda abstraction, what are free variables? If you have 0 here, if you have 0 here, 0 is not free variable because 0 corresponds to this lambda binder. So now free variables have indexes greater than or equal to 1. So we use a subscript 1. Let's repeat one more time. So tau 1 I some expression. So the meaning of this function is find the free variables here, and these free variables have indexes greater than or equal to 1, and you want to shift them by I. Now suppose that you have a lambda abstraction here. Then we want to move this tau function inside the body. But here, 0 is, of course, pointing to this lambda binder. So now because of this new lambda binder, a free variable should have, because of this lambda binder, free variables now have indexes greater than or equal to 2. So we use 2. So these two examples illustrate that we need a subscript here to indicate, to tell whether a given index is free or not. So finally, we have this generalized form tau j I n. But the meaning of this function is find the free variables in n. Then what are free variables? Free variables have the Brown indexes greater than or equal to j. So j comes from here. And then once you find the free variable, shift the free variables by I. And where do we get I? From this superscript I. So that's the informal description of this function. Then let's derive the equations for this shifting function. So this is the easy case, tau j I and 1 and 2, and we just propagate tau j I and 1 applied to I and 2. Now what about this lambda abstraction? So the meaning is all variables, free variables in this expression should have indexes greater than or equal to j. Now we'd like to move this tau function inside this lambda abstraction. So now you have tau I n. Now inside this expression n, free variables should have indexes greater than or equal to j plus 1 because of this lambda binder. So now you have to use j plus 1. In other words, free variables inside this expression n should have indexes greater than or equal to j plus 1 because of this lambda binder. Then what happens if this is the Brown index? If k denotes free variable, from the informal description of this function, free variables have index greater than or equal to j. So if k is a free variable, k is greater than or equal to j. So in this case, you have to shift it by I. So you add I. The remaining case is, what happens if k is not free variable? That is, k is less than j. In that case, it's not a free variable, so it's a bound variable, so you don't make any change, so it's going to be k. So this concludes the definition of this shifting function tau. So we have 4 cases, and we go back to, with this definition, with this function, shifting function, we go back to the substitution function. So now the substitution function is correctly defined using the shifting function. Then, even in the presence of free variables in n, we can complete this substitution.